Yeah, thank you. Hi, everyone. Thanks for the introduction. My name is Tiia-Maria Pasanen. I'm from Finland. I'm a PhD student in statistics in University of Jyväskylä. And today, my topic is, as already said, a Bayesian spatio-temporal analysis of markets during the Finnish 1860s famine. This is a joint work with my supervisors, economic historian Miikka Voutilainen and statisticians Jouni Helske and Harri Högmander. So what I'm going to talk about, first I'm going to introduce the context of the Finnish 1860s famine. Then I'm going to tell you something about the data I have been using. Then we're going to go through the model we have been using. So first the traditional error correction model, and then how we generalized that. I'm going to show that step by step. And then, since this is very application-driven study, I want to, of course, show you some results we got. Okay, so let's start from the context. First, let's do a small time travel. Let's imagine that we are in Finland, in very rural country, back in the 1860s. And for some reason, there are really bad weather conditions. It's raining too much, or it's too dry, it's too warm, or it's too cold. And because of that, we lose crops. And that happens not in all areas, but in some in Finland. And that continues year after year, not always in the same areas, but in some parts of Finland. And that lasts the whole decade, and because of that, we lose half of our crops. And because of that, we don't have food to eat. So there is a huge outbreak of famine then. Here you can see a figure that is from a magazine of that time. There you can see a family that is starving, and from the window there's a view of a man peeling a pine tree in order to get at least something to eat, because that's what people used to do back then. Okay, so originally there were around 1.8 million people in Finland, but because of the famine, almost 200,000 deaths occurred. Some of those were actual deaths, people dying, and some are just absences of birth. But about 10% of the people died because of the famine. This can be considered as the last peacetime population disaster of Western Europe, which in itself is not such a great merit. But since something so tragic could happen so close to the modern times, people kept track of many things, and we have recordings, we have data. And now let's see what kind of data I have here. So, of course, my data comes with 2 dimensions because this is spatio-temporal modeling. So first, let's go through the space dimension. Here, you can see a map of Finland. The width is approximately 500 kilometers, so that you can think how wide this area actually is. There are these white areas. There are 48 of them. Those are administrational districts that are rural or countryside. And then additionally, there are 32 towns. Those are the blue dots on the map. And since I have to model somehow this spatial thing here, I have to define neighborhood somehow. So I consider 2 sites sharing border neighbors here. So that means that those blue dots or the towns, they have usually 1 or at most 2 neighbors. And then the white areas, the countryside has more than that. And then what actually happens on all these areas, let's go to the temporal structure. On every site of these 80 districts, there is a marketplace or several, but at least 1. And then some local administrational person, maybe a priest, goes to that market and writes down what was the price of some products, rye, especially in this case of mine. And writes it down and sends the report to the Department of Finance. And then those reports were stored in the Finnish National Archives in Helsinki, which is the capital of Finland. It's here in the south. And now I have this data. This reporting was done monthly. So I have data from January 1861 to December 1869. Overall, 108 time points from all these 80 districts. This gray area here in the north is called Lapland. It's not included in my study. I do not have data from there. Then I want to show you a glimpse of the data. Here, the black curve is the average of the rye prices as Finnish marks per barrel. And then the shaded area is the 95 percentile here. There are two peaks, one there around 1862, 63, and another, a bigger one, during 1868, which can be considered as the worst peak of the famine. But during the whole decade, there was that famine occurring all the time. But yeah, the prices got really big in those 2 points. Well, the actual question here is that since some areas were suffering more than the others, I would like to know if there were working markets. Could the not so much suffering areas alleviate the famine on the other areas? And in order to find that out, I need some kind of model. And I use error correction model that is traditionally considered in econometrics. This error here is not the error that we as statisticians like to consider, but this is just the difference between time series. And the correction is actually like how those time series want to find a balance. This whole model is made to model how two time series try to find a common balance. And yeah, let's go through this model, what's in this. On the left-hand side, there is time the difference of prices between this and previous ones, just in this site. And then that difference, price difference, is been trying to explain with some components. And let's go them through piece by piece. The first one, alpha, stands for common trend for both those sites, now that there are just these two sites, I and j. And then this beta denotes the short run effect. It tells how the difference in neighbors this and previous month's prices affects to this site. And then the actual error correction term gamma, it denotes the effect of difference between this and its neighboring sites prices. And then, of course, at the end is the error that I like to consider as real error as a statistician. Okay, well, this is the basics, the base for that everything is built on. So first thing that I would like to do to improve this is to consider several neighbors simultaneously, since my sites always have one or more neighbors. And in order to do that, I can just add these betas and gammas, the short-term and the long-term coefficients, and then I get these sums that are here. I use the same color coding all the time so that it's easier to keep track. The sums go just over the neighborhood of the site I. The capital JI means the neighborhood. Then I can now fit the model for each of those 80 districts separately, but I would like to compare them somehow. And in order to do that, I should set some kind of reference level or do something else. I didn't even know what to do. So I want to skip that comparing thing completely. And that's why I fit these models for all the 80 regions simultaneously. And in order to write that down, I need these matrix notations. So let's go through these. I try to explain what happens here. The bolded letters are now vectors. They go through all the sites, but as the time index there shows, it's just one time point. So the price of this month is explained with trend as before. It's there. It hasn't changed at all. It's just one constant for all the sites and for all the times at this point. Then I collect all the coefficients that consider this month's prices and gather them in this matrix B. And then I take all the coefficients that are related to the previous month's prices, and then I gather them in the matrix D. And these matrices B and D are not interesting in themselves. They are here just for computational reasons. So actually the betas and gammas are actually the important coefficients. Then I want to make this model a bit more sophisticated by adding time dependency on the trend component, the alpha, so that it can actually be considered as trend. And then since the regions come with different sizes and locations and population densities and weather conditions and whatever, I do not want to make them follow the same trend. So I add site-specific spatial weights for them, and they are these lambdas here. And then, since I'm especially interested in these error correction terms, the green ones, the gammas, I want to add a time dependency for them, and that's why there is a time index with the matrix D. Okay, then there is just one more thing I would like to do, because the data comes with different kinds of errors, like there were people actually writing it down and it's very old and the currency is changed. So I would like to consider this new here just an expected price, expected value, and add one latent layer here. So the actual observations come from a normal distribution that has this mu as its expected value and then just some covariance matrix. Now we have the model, and in order to estimate this, I have to make a lot of assumptions. Here are some of them. First of all, the trend is assumed to be a first-order autoregressive process. Then we assume the error correction terms are random walks. And then there were those intensity parameters, these lambdas that were adjusting the trend. We set a prior for them so that the prior median is 1, and that is done in order to get this term to make it identifiable. And also it enables to interpret the alpha as actually a common trend for all the sites. Then in the original error correction model, they assumed that those short run coefficients, the betas, are between 0 and 1. We restrict them here to be just positive. Let's see later what happens with that. Then the original error correction model also assumes that the error correction terms, the gammas, are between -1 and 0. And we do that here too. And then this whole Bayesian estimation is done with STAN in RSTAN actually. And it takes about 11 hours to fit this whole model. Okay, so let's see the results. Here are the expected prices according to the model. The blue dots are the actual observations, and then the black line is the posterior mean, and the shaded area is the 95% posterior interval. These are on logarithmic scale, and there are just 3 sites that are located on different parts of Finland. One is on the top one is on west, and the middle one is in south, and the bottom one is from east. As you can see, these look quite nice, these expected prices that we get estimated. Then here are the betas, the short run coefficients, we restricted them to be just positive, but as you can see, they are quite nicely between 0 and 1, not completely, but close enough for practical purposes. And that's nice since we didn't give them a upper limit. These coefficients consider always one pair of neighbors, and now they have been grouped in 3 different groups. In the top panel are the coefficients where the site itself and its neighbor are both rural sites. In the middle panel are the sites where the site itself is rural, but its neighbor is urban. And then the bottom one are the coefficients where the site itself is urban, a town, and its neighbor is rural. And as you can see in the bottom panel, the coefficients are the largest. And that can be interpreted as those towns being most affected by their neighbors, which sounds reasonable since the towns didn't produce the food. It was produced in the countryside, in the town's neighbors. So it's very natural that the neighbors affect more to the towns than to the other sites. And then to visualize all this on a map, we did some shock simulations. This means that we calculated the prices, expected prices for all these sites according to the model, so that initially we set same price for all the sites, but on one site, and it's colored here on dark blue. And for that site, we set 1% increase in the prices. And then we assume the trends and the errors are 0, and take the betas as they are. And then the error correction terms that did depend on time, we have to fix them to be from a certain time. So we choose them from the July of 2 different years here, 1861 and 68. The 61 is like pre-famine. The famine is not going on really badly then. And then 68, since the famine is peaking then. And let's see how much the price shock affects. So this Moscow is a rural area here. It's countryside. They produce the food there. Yeah, I forgot to say that the simulation covers a year, 12 months, but I hope you got it there. Yeah, this is during the famine. As you can see, the effect is quite wide, and during the famine, it's wider and stronger than before the famine. Then, to compare it with something, here is a town, Turku. It's a neighbor, that previous site. And well, the simulation is the same, but let's see what happens in this town. And during the famine, as you can see, that was quite mild. So the effect of this town was wider before the famine than during it. And that is also very natural, since this Turku didn't produce that food, but it was brought from outside. So if the prices got bigger in Turku, then it didn't affect to the neighboring sites. And from all this, I would like to conclude that actually there were some market integration. The markets worked, at least on some level, already back then in Finland. Yeah, that was pretty much all. Here are some references. Yeah, thank you.
Thank you, Tiia-Maria. And now we have a space for several questions. So it seems that in the chat, I do not see any questions and I do not see any raised hands.
May I just add one question, Jan?
Yes, Andrei, please.
Thank you. So there is also Alexander, I think, who been in the audience, but a clear thought. It was a very nice presentation on using Bayesian spatial-temporal modeling and having 11 hours, as you mentioned, for convergence. Have you considered integrated nested Laplace, INLA? Usually this speeds up computation, but also, as I mentioned, Alexander and others in the audience can comment.
Yeah, that's a really good question. Thank you. We have been thinking that, but there is a limited amount of hyperparameters in that, and we have there are almost over 100 time points and 80 districts. And since there are many coefficients that depend both on time and space, there would be just too much parameters, but that would be really nice to be able to use INLA here too.
Thanks. Maybe something to speed up the computations would be valuable. Thanks.
Anna Martins has raised hand, so please.
Thank you. Tia, thank you very much for your presentation. It was really nice. My question is very basic, probably. My question was, what was the criteria that you used to define what is a neighbor or not? So sharing borders or so other? Would you like to comment on that, please?
Yeah. Good question. Yeah. We considered the two sites as neighbors if they shared border. So just one common borderline point was enough for them to be neighbors. Yeah.
Thank you.
You're welcome.
Any other questions from the audience? Eve, please.
Yeah. Great talk, Tia, thanks. Just a quick question. So it looked like you used, was it rye for your, I'm going to say, your crop? Would you expect, was there other crops to be similar, or would you think they'd be quite different, was they going through time?
Good question. I haven't actually analyzed the different crops, but we assume that they would work somehow similar to this. The rye was chosen because it was the most common grain back then, but we expect the other ones to work a bit similarly, but have more effects during the worst famine years, because then the people should use something else than the rye. Yeah, good question. Thanks.
Brilliant. Thank you.